This is video 3. Okay, let's have a look here. So this is B5 from the mock exam. The what? Yeah. Y equals 24x cubed minus 18x4 plus 8. Find dy dx. So that would be 72x squared minus 72x cubed. Is that okay so far, Mo?
Yeah.
Right, part B now. One sec, I just need to get the attendance here actually. Right, part B. Guys, listen please.
Full attention.
Now, part B, show that there are stationary points when x is 0 and 1. So when you calculate dy dx at 0, you'll get 72 0 squared minus 72 0 cubed, which is 0. And when you calculate the derivative at, what was the other point? 1, wasn't it? That's 72 by 1 squared minus 72 times 1 cubed. That's also 0. So, therefore, stationary points. Are you asking me something or what? Good, good. Yes, questions? Oh yeah, that's another interesting way to do it. If you were to, you're saying if you were to factorize here into 72x squared by 1 minus x, then clearly the two solutions are 0 and 1. Yeah, that's fine too. Okay, shh, listen. C. Now, this is the, yeah, well, maybe. This is the trickier one. Confirm there's an inflection point at 0 and determine whether there is a maximum or minimum at 1. So first let's look at 0. Either way we'll need the second derivative. So the second derivative here, let's see, it's going to be 144 x minus 216 x squared. Now, we were asked to look at 0 first. Yeah, if you put in 0, obviously here you get 0. So in situations where the first derivative and the second derivative are both 0, we need to have a look at the third derivative. So the third derivative here, and that will be 144 minus 432x. Now, if you put in the third derivative at 0, you'll get 144, which is positive, which is therefore a rising inflection point. And we repeat the process. I'm sure the second derivative is going to be 0 again. So what I'm going to do is, this is the first part when x is 0, and then this is the second part now when, what's it, 1. So if you put in 1, oh, it's not 0, okay. Oh, because it's not an inflection point. It's, let's see what we get. It's obviously negative. So that makes it therefore a local maximum. Yeah, that's all reasonable amount of work for 5 marks. You don't need to, because they only asked if it was a max or a min. It's at least a local maximum, but it actually, I believe, will turn out to be a global maximum when we draw the graph. Yeah?
No, why is it not a local minimum?
Because the second derivative is negative.
That's
process. What's going on right now? Have you forgotten how second derivatives work?
Second derivative is 0.
It's not.
No.
One is not.
No?
That's 1.
Yeah.
Do you know what's going on?
I thought it was 0.
The first derivative needs to be 0, which it is. And the second derivative needs to be negative, which it is. So it's max.
But why did you choose 1?
Because they told me.
It says at x equals 0 and at x equals 1.
Oh,
Read the question.
read the question, of course. Okay, D. Can I scroll down to D?
Yeah.
Okay, so if we look at D now, they ask you to draw this. Now there's a couple of points we know already. We can put in 0, and what value for y do we get when we put in 0? If you look at the original, you can see that y will be 8. Yes? So if I put in 0, I have a point here at 8. And then what was the other point of interest? It was x equals 1. And if I put 1 in, let me calculate, that'll be 24 minus 18, which is 6. 6 plus 8 is 14. So 1 and 14. So here are my 2 points. This one here at 0, 8, and the other one is 1, 14. Now you know a couple of things about the shape. You've just worked out at 0, 8 you have what? Rising inflection. And at 1, 4 you've just worked out it is a maximum. So if you were to draw this, we need to have a rising inflection, so that goes from concave to convex, and then that feeds into a maximum. That's not great, let me try that again. So,
Choose 4.
You have to start before the y-intercept?
a little bit before it, yeah, just a little bit. Now they actually say don't cross the x-axis in the picture, so this is what I think they'll have in the marking scheme.
That's a cubic.
Yeah, it is.
No, it's not. Oh, it's power 4.
Yeah, well,
Yeah, that's not cubic.
Oh,
It looks like a cubic, but it's not. It's not actually quite a cubic. These cubics can't make this shape. At least I don't think they can. Yeah. It's okay.
you got my point though. It has 3.
No, it doesn't. I'm sorry. That's not. There's no turning point here. It's 2 turning points.
Oh,
Yeah. It's really difficult to draw this because you need to make it a rise and inflection and then a max. Yes, it is very ugly. So here, just to be clear, Amjad, this is a concave shape. Okay. This one here is convex. And then this is a local max. And this is concave again. And this here is stationary. What I mean by that, it's flat. Now, if you think about it, this is concave, this is convex, and this is concave again. So I kind of feel like there might be another inflection point here. Now, they don't ask you to find it. So what I'm about to do next is optional. But just to test this out, I kind of feel like there'd be an inflection point a little bit before 1. That's at 1. So what was the second derivative? Did anyone write it down from earlier?
Yeah, it's 72x squared
Yeah.
minus 72x.
No, that's the first.
Oh, okay.
Minus first.
Yeah, minus
144x minus 216
x squared.
x squared. Inflection point requires this to be 0. So what do we get here? I could factorize this. I could take out x, couldn't I? And I'm left with 144 minus 216x. There's one inflection point at 0. We knew about that one, where it switches from being concave to being convex. But according to this, there should be a second inflection point at x equals 144 over 216. That's exactly what I just said 1 minute ago. I said it looks like there'll be an inflection point slightly before 1. So what is that as a decimal? 2 over 3.
6, 6,
Okay,
6.
there you go. So it's an interesting question because you didn't even find all the inflection points on the graph. There was one more that actually existed, but you don't need to find that.
Sorry, but when you actually graph it,
Yeah.
Hmm?
when you actually graph it, it doesn't show a second inflection point.
Are you sure?
Yeah.
Now, what resolution is that? 320 by 240 pixels? Or
No, I zoomed in.
can you pass that up? I want to see what it looks like on your calculator.
Pass it,
Oh man, that is messed up. No, sorry. That's never going to show it. It's not high enough resolution.
Maybe we want.
This is very easily figured out, Mo. We'll graph it here. And then there's a last part to do. Yeah.
No, you can just here just want to see something.
Just open this up for you to have a look.
Are we gonna continue with like exam questions after?
I will see what we'll do. I'm just trying to graph this for Mo because his graphing calculator is low res. Here we go. Okay.
this one time when I have my number.
24x cubed. Is it HD?
Yeah,
It's this one.
it's this one that I have, yeah.
Minus 18x4 plus 8. Okay. My x-axis needs to show. Yeah, about that. And how high do I go on my y? What was my 14? Yeah, so like this. Okay, so let's graph this. Now you can see this shape is concave. Guys, are you looking up over here? Here's concave, and then it levels off here. So this is a stationary point, right? But also, this is concave and this is convex. So this is not only a stationary point, but it's also an inflection point. And we call that a saddle point. Yeah, now all saddle points are inflection points, but it's not the other way around. Yeah. Now, this is convex, but what's this shape here? Concave. So there must be an inflection point here where it switches. But is it stationary? Is it flat? Level? No. So the first derivative won't be 0 here, but the second derivative will be. Yeah. Now, I think it's good for education to just look at this graph to help clear up what's happening with the first and second derivative. So tell me, first derivative, what is it here? Positive, negative, or 0? Positive? Positive?
Negative.
Now
0. And then here? Positive, positive, positive. Well, here's 0 first and then negative. So there's two places where the first derivative is 0. That will be here and at 1. Yeah. These are called stationary points. They are stationary points. Right. Let's look at the second derivative. So second derivative, positive or negative here? So it's a concave shape, so that makes it, who remembers, positive or negative? Negative. So second derivative is negative, 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 and then here, 0. And then positive, 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 and then it actually hits 0 again, because it's going to become negative now. Okay? So you have an inflection point here and here. If this is an inflection point and a stationary point, we call it a saddle point. Okay?
Wouldn't the second inflection be more around 1 rather than like 0.75?
No, because we worked it out exactly. It was 0.667. So it's literally right, like, here. Okay?
It still looks like it's going up.
No, inflection points are switching between concave and convex. It's not about going up or down. So like, if you were to zoom in here, how do I do set on cross or focus on cross? Where is it?
Whose door is now?
There, where is it? There's some option where you can, oh no, it's one of these buttons, sorry. Center on cross. Where? Center on cross, there we go. Now let me zoom in. Does that zoom in? Zoom in. Now I've zoomed in to try and help, but let me, whoops, not that way. I don't know if that helps, but here you can see it's convex. Clearly here it's concave, so there's an inflection point somewhere here where it's switching between the two. Yeah? Okay, so we'll continue now. Last part here. Woohoo. No. Boom, boom, boom. No. Okay. Is that scale a little bit better? You can kind of see it a bit more here. Convex, concave, inflection point there. Right, the last part, E. The student calculated this derivative, antiderivative, 24x cubed minus 18x4 plus 8 dx, and they got minus 4 and 21/80ths. Explain why they're wrong. Well, if you look here, this integration is actually equal to the area from 0 to a half. So if you look at the picture, that area between 0 and a half, it can't be negative. In fact, you can actually estimate it because it looks like it's roughly a rectangle. No, it's not a rectangle, it's just roughly a rectangle. How big is the base? From 0 to a half?
0.5.
0.5. And the height? The height?
8.
8. So what is this area here roughly?
4.
It's roughly 4 units. So if you were to look at this, you would say it's roughly 4 units. Now the fact that the students said they got minus 4 and 21/80ths means that they probably got the right number but the wrong sign. So you would say that would mean likely right value but wrong sign. And how does that usually happen? I.e., they probably did actually the limits backwards.
Yeah, he minus 0 first.
Yeah. Yeah. Or she.
Yeah, she.
Either way. No, be careful now. I was applying the error to genders equally now, so it could have been either.
It doesn't start with A.
I'm telling you, this student now is Arab because they have the signs backwards. It's a common mistake. Right to left, left to right. Okay, E part 2 now. So the student calculated the tangent at a half, x equals a half, and they got y equals minus 9x plus 5 and 3/8. Now you notice that here they're saying that the m is negative, which is the same thing as saying dy dx is negative, because that's the slope of the tangent. If you look back at the graph, where is point a half? It's rising. It's rising. So the first derivative should be positive. But what you can say, but at x equals a half, y is rising. That means the dy dx should have been positive, not negative. So again, another sign error. Yes, okay, yeah. Yes, indeed. Okay. Right, so I actually think, looking back at this question 5, it was actually, I think you would probably prefer doing this than the area and volume. Yeah, where you're given a greenhouse or a can or, yeah, okay. Because there's not anything too difficult about this one. Yeah? Okay, so we can have a look at something else now. Let me just open it up here.
Can you do a question?
Yeah, let me just save this. Cancel that.